In this video we're just going to talk about the inverse square law experiment, the specified practical. So to start off with, here's the apparatus. You can see we've got a gamma source here, a Geiger-Müller tube detector and digital counter attached to that, and then a meter ruler to measure the distance between the gamma source and the GM tube. Okay, and what we're going to look at is how does the distance, so the distance d between these two things here, how does that distance affect the count rate on this counter? So the count rate is the number of counts per second, or the number of counts in 100 seconds, or whichever unit you choose to use. So to start off with, let's just think about what's going to happen with this gamma radiation. So if you take this gamma radiation here, it's going to emit radiation in all directions. Okay, so it's going to emit radiation in every direction. And on the paper, obviously, it looks 2D, but in reality, it'll be 3D. So the radiation will proceed out from the gamma source in a 3D, obviously in all directions. And if you look at the radiation at a particular distance from the source, so let's call this distance here D, and let's just get rid of that. Let's just call this distance here D. And if you look at the radiation at a distance d from the source, it's actually spread out across a sphere. Okay, now that means that the radiation is spread out across the area of a sphere, and the area of a sphere is A equals 4 pi r squared. So the radiation emitted from a gamma source is spread out across the surface of a sphere. It becomes less and less concentrated as you get further from the source. So if we've got a source of power P, okay, as I said, the radiation is spread out across the surface of this sphere. This comes out in all directions, okay. Right, now the further you get away from the source, so we'll call that distance there D. This distance here we'll call D1. The further you get away from the source, the more spread out the radiation is, so the less intense it is. Now intensity, I, is equal to the power of the source divided by 4 pi r squared. Okay, because intensity is equal to the power of the source over the area over which it's spread out. Intensity is measured in watts per meter squared, or watts per meter squared, maybe we should put it like that. Okay, power is measured in watts, and obviously area is in meters squared. So what we've got here is watts over meters squared. So what we're saying here is the intensity of the radiation at a certain distance from the source is equal to the power of the source divided by the area over which that radiation is spread out, and in this case it's a sphere. Now notice here we've used D for distance, but in the usual equation for the area of a sphere we use R, so we can again rewrite this equation if you want like this: I equals the power of the source divided by 4 pi D squared. Okay, so what this tells us is that the intensity is directly proportional to 1 over the distance squared. Okay, the intensity of radiation from a gamma source is directly proportional to 1 over the distance squared. This is in inverse square law. Okay, as the distance from the source doubles, the intensity will reduce by a factor of 4. Okay, because it's an inverse square law. So as the distance from the source doubles, the intensity will reduce by a factor of 4. Okay, so that's the first thing to say. Now the next thing to say is this: that the count rate of a gamma source is proportional to the intensity. So we won't go through all the maths here, but you can figure out, you can basically show that the count rate of a gamma source at a particular distance from that source, okay, so the count rate at a particular distance from the gamma source is directly proportional to 1 over the distance from the source squared. Okay, you can show that because the count rate is proportional to the intensity, so the count rate at a particular distance from the source is proportional to 1 over the distance squared. Okay, because again, if you think about it, the count rate is to do with the amount of gamma radiation detected in a certain period of time, and the further you are from the source, the more the gamma radiation spreads out over the surface of a sphere, so the lower the number of counts that you're going to detect for a particular per meter squared at that distance. Okay, so there we go. Now, the next thing to say then is we are told in our experiment method that we're going to investigate this relationship. Okay, we're going to investigate C is equal to K d to the power of n. Now, having looked at this equation here, or this relationship here, we know that we can write C is equal to a constant divided by d squared, so we can write that, okay, which also can be written as C equals K d to the power of minus 2. So you can see that these two equations here are somewhat similar, okay, and in fact they're identical in many ways, apart from the fact that we've written this as n instead of minus 2. Okay, so this is the equation that we're given by WJEC, and we know that n is actually going to be equal to minus 2. We know that that should be the case, okay, because we can see it here. We know it from the mathematical analysis that we've done here, okay. So what we're asked to do in our experiment is to work out values for k and n, and in the next video I will show you how to do that.